I knew that had to make
Chemistry time. We're talking about covalent bonding. Well, let's break the word down first. We already, coincidentally, in a completely different context, talked about valent today, but here, valent is going to be the answer you provide. What does valent mean in this word? Referring to what? Yeah, the valence electrons. Say it a little louder so the blue Yeti mic can hear you.
Valence electrons.
Okay, well you made me misspell it because you scared me. Valence electrons. And of course co meaning what? What does co mean when it's in a word like this?
Together.
Together.
Together valence electrons.
Yeah, so right, the syntax is wrong, but basically as opposed to what other kind of bonding? What are the two kinds of bonding? Ionic and
metallic.
as opposed to ionic, where they did what? Yeah, one gave its electron or electrons to the other, and that other one accepted it, and then they both were charged, so they combined. Right? That's how ionic bonding works. Do you remember that?
Yes.
And opposed to metallic bonding, where the valence electrons were just kind of scattered willy-nilly about all these cations. In covalent bonding, what's the verb we usually use for this? It's a nice little cute word. What do they do with their valence electrons?
Share.
Oh. They share. They share electrons. They share electrons. So, all of this is still governed by the electromagnetic force. All of this is still governed by the electromagnetic force, except here, obviously it can't be the attraction between a cation and an anion, because instead of giving and taking, they're sharing. So no ions are formed. So put that in your little brain pocket. No ions are formed. There's no ions, and that's why we don't call it ionic bonding, right? Remember, an ion was when one gave and another one took. So this is a completely different thing, but it's still governed by the electromagnetic force.
No giving, no taking.
No giving and no taking. They share instead.
So it's like my personal.
So instead of there being two separate ions that are then joined because they're attracted to one another, now it'll be something like, and I'm just going to draw oxygen, for instance. So here's oxygen. Here's its little nucleus. How many valence electrons does oxygen have? Let's all try to be right. Six is the correct number. So how many does it have in its first shell?
3.
Nope. Two. And then in the next shell? 6. And I say shell, it could be orbital, energy level, any of that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, yeah. Good. So now, these are two separate atoms, right? They're not ions because they don't have charges. They are separate atoms. I'm just going to draw it again. Now, what happens in a covalent bond, I have my eraser right here. What happens in a covalent bond is that what about this atom could be attracted to what about this atom?
The nucleus.
Yeah, okay, good. Yeah, I'm kind of surprised you got that fast, but yeah, the electrons of this atom, because they have what charge?
A positive.
Oh, goodness, yeah, a negative charge. A negative, what?
Rose.
That's not how you draw a negative. The electrons, each of them has a negative charge. And just because of the way they are, because of the way negative and positive charges work, each of these electrons is attracted to the positively charged nucleus of the other one, right? So it's still the electromagnetic force, except now instead of an ion being attracted to another ion, and the whole thing's being attracted, now it's electrons of one being attracted to the nucleus of the other. And guess what? The electrons of this one are also attracted to the nucleus of this one. So now, so they still have two inner electrons that they keep for themselves. But now they're all sharing how many? 12. They all are sharing 12 electrons.
Attracted to each other's.
And this isn't, strictly speaking, quite true, because what really happens, it's easier to see in this notation, but we have, once again, if we're going to do an electron dot diagram, how many valence electrons should I draw around the oxygen?
2. 6.
6. 1, 2, 3, 4, 5, 6. And then the other one, same thing. 1, 2, 3, 4, 5, 6. So they have the same number of valence electrons. How many do they want, remind me? 8. And do you remember the name of this principle? They want 8 valence electrons, and that's called the what rule?
Oh, the weird one.
Octet rule. They all want 8 valence electrons. That's called the Octet Rule. Anyway, so in order for this one to have 8, how many will it have to share with this other one? How many will have to be shared to it, that is? 2. So they're going to share how many altogether? 4.
Wait,
Oh, I remember doing this.
so that makes more sense than that one. Because
Right,
that
right.
one, it shows that it's sharing 12 and it doesn't
Right,
plot.
right, exactly. So I'm going to redraw this one.
Okay, so
It's just kind of hard to see in that format, so I was going to redraw it like this.
Okay.
So this one, all of these, I'm going to use different colors for this. They're both oxygens. All of these electrons are like they belong to this oxygen. It doesn't matter who they belong to, or I shouldn't say who. It doesn't matter what they belong to. How many does it have now? 8. Okay. And then this one, it's like they're sharing this. Oh, look. So it's like this one has 8 too. Once again, they're both oxygens. I'm just using different colors that represent different atoms. Each of them has 8. So how many are they sharing?
You just confused me.
Well,
No. How many are they? Just the ones that they're sharing, not how many they have all together. They're just sharing 4. So each one it's kind of like it keeps 4 of its own, and then it's sharing 4 with the other.
How is it sharing 4? Because if they had 6 and they're sharing 4.
So once again, there's still a total of 12, but these ones overlap. They're being shared both to this one and to this one. That's why I drew them like this in this nice Venn diagram kind of format. What's this all called?
Tyler, you don't remember this stuff?
I remember.
Yes, but what's the whole thing called? They're satisfying the Octet Rule. Covalent bonding, right? They're bonding covalently. They're sharing valence electrons. So here's the next question. Why don't they, if these electrons are attracted to this nucleus, why don't they just smash right into each other?
Opposites repel?
Yep, exactly. Tyler, you're really on a roll today. Yes, because, and also that's not how it works, and that's true, but she's being specific enough to satisfy what I was asking. While the electrons and nucleus of the electrons of one and the nucleus of the other attract because they're opposites, when they get close enough, the nuclei start to get close together, and they don't want to be close together, right? Because they're both positive. So there's a repulsive force. Repulsive, and what's causing this repulsive force? Say it again. Yes, still the electromagnetic force. So the electromagnetic force is both holding them together and keeping them apart, right? It's holding them together because they're attracting because they're opposites, and it's pushing them apart when they get to a certain closeness because they are the same, right? Because the nuclei are the same.
That's like us.
That's just like us, right? Yeah. That's a good example because you want to get close to someone who's kind of the opposite to you, but when you get too close, you have to push back a little, right? They can't be in your. Oh, let's not.
It's like my mom.
What?
No. They can't be your soul. Look at this little sad face I made. Let's move on. Okay,
Oh, Natalie,
let's
don't
move
make me
on.
cry.
Let's move on. So now this one shared how many?
4.
4 valence electrons shared.
Yes.
Okay, now here you're going to do a little bit of math. How many pairs of electrons is this?
That's
2.
2 pairs. So write that down.
Oh, that's wrong.
Because of the way sharing works, it's always going to be in pairs. We talk about 2 pairs of electrons. Let's do another example here.
What did I say?
Instead of
4 valence electrons shared.
4 valence electrons shared, and that's 2 pairs. You see it on the screen? Yeah.
Force.
I'm going to erase this too. So now, let's do the same thing, but with, let's pick another element. Let's pick a halogen. Find me a halogen, please. Which one?
Bro.
Bromine. Good. How many valence electrons does bromine have?
7.
And how many valence electrons does bromine have?
7. So they have to share 2.
No, it doesn't have to be the same element, but yeah. How are you guys knowing all this
Well,
already?
because if they both need 2.
Right,
No, they
exactly.
need 1, so together that
Yeah.
makes them share 2.
Mhm.
Because altogether they need 16, and altogether they've only got 14. So
there's
only
only
what's
one
the
pair.
difference?
You're actually very good at this. I don't know how, but good job knowing this
So
without
one
even having
pair.
me teach you. So 1 pair. And then lastly, we're going to do one like this.
Oh, was that hard?
Yep, nitrogen. How many
That's-
valence electrons does nitrogen have?
5.
That's 5.
Oh. So they
So-
each need 3.
Okay, so.
So that'll make 6.
Mhm.
So it's
3 pairs?
no. It's only
How many are they sharing? I can't see.
They're sharing 3 pairs, which is 6 valence electrons.
Yeah, so 3 pairs.
Wait, why is there still 2 on the outside?
Right, so they can't ever share all of them. They just can't. I guess there probably is a reason that I've never actually thought about, but there is no such thing. We're going to name each of these in a second, but there's no such thing as them sharing all 8 of their valence electrons. It does not. It cannot happen. Do you know why? No, neither do I. There is a reason, but I don't know it. We have names for these. When it's one pair being shared, we call that a. Can you guess what kind of bond it is? It's covalent. What kind of covalent bond? It was one of your vocab words, I think. Nope, it wasn't. We call it a single. This sharing of 2 electrons is called a single covalent.
2 pairs or 2 electrons?
2 electrons, which is 1 pair. So single covalent bond.
1 pair is single.
What if they share 2 pairs? Can you guess what that might be called?
Double.
Good, yeah. A double covalent bond. And in the case of nitrogen, triple.
But they can never share 4 because that'd be 8 and you can't share all of them.
Right, there you go.
Okay.
You can't share all of them. She's just right.
It's called self-care.
It's called... Hey, that's... I don't know. You guys took your chemistry Wheaties this morning or something, but you're doing a great job.
This stuff is easy.
Oh,
We like this stuff.
I guess I didn't think so when I learned it, but I'm proud of you for thinking it's easy.
You know how good
Let's talk about this real quick. That I don't think that's true, but thank you for saying so. Let's talk about this. If and we're just gonna this gets a little bit deeper, but we're just gonna say this. Just a single covalent bond is called a sigma bond. That's another name for it. Sigma is a separate kind of type of bonding, but when it's just a single bond, the type of bond it has is a sigma bond.
Yeah, that is one of my vocab words.
Sigma.
Sigma bond.
Sigma
is a
bond.
single
And
bond.
the Greek letter sigma looks like this. It's like a little...
Leaf blower.
Okay, sure. Sure, that's actually what the Greeks were thinking of when they shaped it this way.
Really?
No. What? No. A sigma bond looks like that. No, it doesn't look like this. This is the letter we use to represent it. And then when there's a double bond, that's a, why did I use a different color? It's a sigma and a pi. 1 sigma plus 1 pi. You already know the Greek letter pi. What's it look like?
It's like it always reminds me of like a cursive R doubled.
Okay, sure. I draw it like that.
I gotta think real hard.
I can't
when
see
draw
it.
the sigma.
Wait, how do you draw that sigma? Looks like a leaf blower.
It's like an O with like a little curly Q.
Yeah.
And then the triple is 1 sigma again and 2 pi's. I'm going to just read you what your book says about sigma and pi bonds. And for me, for the test, this what I've written up there is good enough, but listen to this. Single covalent bonds are also called sigma bonds, represented by the Greek letter sigma. A sigma bond occurs when a pair of shared electrons is in an area centered between the 2 atoms. That makes sense, right? Pi bond. A multiple covalent bond consists of 1 sigma bond and at least 1 pi bond. A pi bond, represented by the Greek letter pi, forms when parallel orbits overlap and share electrons. So basically the sigma is just in between the 2 atoms physically, and the pi's overlap regions that are covered by their normal valence electron shell instead of being in between the 2 of them. And that's, like I said, it's not supremely important that you know that, at least for this class. It will be expected of you when you get to higher levels of chemistry. But for now, this is what I want you to know. Now listen to this. Okay, are you listening to this? Write this down. The longer the bond is, the weaker it is. That is, the greater the bond length, the weaker the bond strength.
You just said it 2 different ways.
I did. I just was saying the same thing, but in 2
Is it
different ways.
because, like, the-
Bond length is inversely proportional. What's inversely proportional mean?
The longer the bond,
The weaker it is.
is it because of the force gets weaker or the energy?
The force.
Okay.
Good. The strength holding them together. When I say bond strength, that means the force holding them together.
It kind of reminds me of almost like a fire. It's really strong when you start it.
There you
and
go.
then,
There's very, very, very many things in chemistry and in physics that are governed this way. But bond length is inversely proportional, meaning what?
It can go either way.
No, not
It means
quite.
they're opposite.
It means if
They're
one goes up, the
proportions.
other goes down, right?
Opposite importance.
So bond length is inversely proportional to bond strength.
It's kind of like you get sadder the longer your life.
Oh, golly. What it's really kind of like is these little rattlesnake eggs. The further away that they are,
Did
the
you call
less...
them rattlesnake eggs?
That's what they're called. The further away they are from each other, the less force is attracting them, right? So if I get them... This needs to go up. Oh, food.
Isn't it bad if you drop it?
Hopefully not, because that's all I've been doing. The further away from... There is technically a force of attraction between them right now. It's just weak, right? Because it's a long length. But when I get them close together, the strength between them gets stronger, right? Kind of like long distance relationship. This is all I don't want to talk about. Last thing you need to know, make sure you know what endothermic and exothermic reactions are. Endothermic are reactions that absorb energy.
Wait,
And exothermic.
Sorry. Specifically, they absorb heat energy.
Do you want
And
to-
exothermic
It
release
Can you
it.
please say that again?
Yep, endothermic reactions are those that absorb heat energy, and exothermic reactions are those that
Release heat.
release heat energy.
Heat energy.
What does it feel like if something releases heat energy? What's it gonna?
Like a
I think
burst
it's
of air.
like cool.
It's gonna no. If it's releasing heat,
Yeah, it's like releasing
no, you're both wrong.
heat.
Yeah, it's releasing heat, so it's gonna feel hot. If it's absorbing heat, it's going to feel
Cold.
cold. Okay, so an endothermic reaction is one that feels cold, an exothermic reaction is one that feels hot. That's that's kind of a gross simplification, but do you have questions about any of this?
No.
Covalent bonding is where they are sharing. And they're sharing because it
Okay.
makes them,
Happy.
Satisfied.
it satisfies there, I erased it, but it satisfies the
Say it a
octet
little
rule.
better than that.
Adios!